Chapter 9. We'll be spending most of the rest of the semester on Chapter 9. We will likely have a quiz on it before the final, and any leftover class periods we have between finishing up Chapter 9 and the final will be in review, ask questions, find out what you're weak on, go over those topics, that sort of thing. So, Chapter 9, Counting and Probability. Introduction to Probability. Imagine tossing two coins and observing whether 0, 1, or 2 heads are obtained. It would be natural to guess that each of these events occurs about 1/3 of the time, but in fact this is not the case. This table shows actual data obtained from tossing 2 quarters 50 times. And you might be able to guess from the data that the general probability is going to be approximately 25% 2 heads, 50% 1 heads, and 25% 0 heads. So, to formalize this analysis and extend it to more complex situations, we introduced the notion of random process, sample space, event, and probability. To say that a process is random means that when it takes place, one outcome from one set, from some set of outcomes is sure to occur, but it is impossible to predict with certainty which outcome that will be. So, if an ordinary person performs the experiment of tossing an ordinary coin into the air and allowing it to fall flat on the ground, it can be predicted with certainty that the coin will land either heads up or tails up, but it is not known for sure whether one or the other will occur. So, we restricted the experiment to ordinary people because a skilled magician can toss a coin in a way that appears random but is not, and a physicist equipped with first-rate measuring devices may be able to analyze all the forces on the coin and correctly predict its landing position. Just a few of the many examples of random processes or experiments are choosing winners in state lotteries, selecting respondents in public opinion polls, and choosing subjects to receive treatments or serve as controls in medical experiments. The set of outcomes that can result from a random process or experiment is called a sample space. A sample space is the set of all possible outcomes of a random process or experiment. An event is a subset of a sample space. In the case where an experiment has finitely many outcomes and all outcomes are equally likely to occur, the probability of an event occurring is just the ratio of the number of outcomes in the event to the total number of outcomes, the total number of possible outcomes. So the equally likely probability formula, if S is a finite sample space in which all outcomes are equally likely and E is an event in S, then the probability of E, denoted P of E, is the number of outcomes in E divided by the total number of outcomes possible in S. For a finite set A, N of A denotes the number of elements in A. With this notation, the equally likely probability formula becomes this right here. N of E over N of S equals P of E. Probability of the events. The number of events, the number of outcomes in the sample space, and the probability of the event occurring. So, an example. An ordinary deck of cards that contains 52 cards divided into 4 suits: diamonds, hearts, and clubs and spades. Each suit contains 13 cards, and the cards Jack, Queen, and King are called face cards. A few mathematicians showed that 7 shuffles are needed to thoroughly mix up the cards in an ordinary deck. That was in 1992. All right. In 2000, some more mathematicians and engineers used a somewhat different definition of thoroughly mixed up to show that 6 shuffles will nearly always suffice. So imagine that a deck the cards in a deck have become, by some method, so thoroughly mixed up that if you spread them out face down and pick one at random, you are as likely to get any one card as any other. What is the sample space of outcomes? The sample space is the total number of possible outcomes. There's 52 cards, and so there's 52 possible outcomes. What is the event that the chosen card is a black face card? Well, there are 6 black face cards, so there are 6 outcomes of the possible 52 that would be a black face card. Now, what is the probability that the chosen card is a black face card? Well, that would be 6 divided by 52. The number of events in the, or number of possible outcomes in the event, divided by the total number of possible outcomes in the sample space, 52. So it would be 6 divided by 52. Outcomes in the sample space are the 52 cards in the deck. For B, let E be the event that a black face card is chosen. The outcomes in E are Jack, Queen, and King of clubs and of spades, or symbolically this here. Part B, number of events is 6. According to the description of the situation, all 52 outcomes in the sample space are equally likely. Therefore, by the equally likely probability formula, the probability that the chosen card is a black face card would be 6 divided by 52, or about 11.5%. Counting the elements of a list. Well, some counting problems are as simple as counting the elements of a list. For instance, how many integers are there from 5 through 12? To answer this question, imagine going along the list of integers from 5 to 12 and counting each one in turn. So the answer is 8. You're just counting, inclusively 5, 6, 7, 8, 9, 10, 11, and 12. There's 8 numbers there. More generally, if m and n are integers and m is less than or equal to n, how many integers are there from m through n? To answer this question, note that n is equal to m plus the quantity n minus m, where n minus m is greater than or equal to 0. Note also that the element m plus 0 is the first element of the list. The element m plus 1 is the second element, m plus 2 is the third element, and so forth. In general, the element m plus I is the I plus 1 element of the list. So the count is equal to n minus m plus 1. And so the number of elements in the list is n minus m plus 1. You see better here. How many 3-digit integers from 100 to 999 inclusive are divisible by 5? What is the probability that a randomly chosen 3-digit integer is divisible by 5? Now, you can write out all the integers and mark the ones divisible by 5, and it's you write them out with each integer with an arrow pointing to its corresponding multiple of 5. There's many 3-digit integers that are multiples of 5 as there are integers from 20 to 199. Right? By theorem 911, I think this doesn't make sense to me. 199.22011. Where did they get that from? But there's like 180 such integers. Hence, there are 180 3-digit integers that are divisible by 5. By theorem 911, the total number of integers from 100 through 999 is 999 minus 100 plus 1, or 900. By part A, 180 of these are divisible by 5. Therefore, the probability that a randomly chosen 3-digit integer is divisible by 5 is 180 divided by 900, or 1 over 5. Analysis of many computer algorithms requires skill at counting elements of a one-dimensional array. Let A1, A2, to AN be a one-dimensional array where n is a positive integer. Suppose the array is cut in the middle at a value AM, so that 2 subarrays are formed. A1 through M and A sub M plus 1 to A sub N. How many elements does each subarray have? What is the probability that a randomly chosen element of the array has an even subscript, if n is even and if n is odd? Array 1 has the same number of elements as the list of integers from 1 to m. So by theory 911, it has m, or m minus 1 plus 1 elements. Array 2 has the same number of elements as the list of integers from m plus 1 through n. Therefore, it has n minus m elements. If m and n are integers, and m is less than n, then there are n minus m plus 1 integers from m to n inclusive. That's the number of elements in a list. For part B, if n is even, each even subscript starting with 2 and ending with n can be matched up with an integer from 1 to n over 2. So there are n over 2 array elements with even subscripts. Since the entire array has n elements, the probability of a randomly chosen element has an even subscript is 1 over 2. So now if n is odd, then the greatest even subscript of the array is n minus 1. So there are as many even subscripts between 1 and n as there are from 2 through n minus 1. Then the reasoning of part 1 can be used to conclude that there are n minus 1 over 2 array elements with even subscripts, if n is odd. Since the entire array has n elements, the probability that a randomly chosen element has an even subscript is n minus 1 over 2n. Observe that as n gets larger and larger, this probability gets closer and closer to 1/2. Note that the answers to 1 and 2 can be combined using floor notation. By theorem 462, way back in chapter 4, the number of array elements with even subscripts is the floor of n over 2, so that the probability of randomly chosen elements has an even subscript is the floor of n over 2 over n. That's about it for the introduction to probability. I was just going to cover the one section today. We'll continue with chapter 9 on Thursday. Hopefully the quizzes will be graded by then. Yeah, we'll get into more counting and stuff later. I think I mentioned something about counting before and how Waffle House used to have a sign on the wall saying there's this many combinations of ways to have your hash browns with the various toppings and various combinations and all that sort of stuff. I was going to look up that, see if I could find that number, and I'll find the parameters of what makes up hash browns at Waffle House, how many toppings they have, that sort of thing, and we'll see if that number is accurate as an example on the side. Anyway, that's about it for the day. If you came in late, let me know and I'll mark you down. I don't think I see anybody that came in late. Have a good day.